Hi everyone, I'm Dr. Vanessa Moreno, and in today's video we're diving into power training, plyometrics, and speed, agility, and quickness. Full disclosure, I am a mom of two, so if you hear a bit of background commentary, it's likely coming from my tiny co-host. So let's dive in. So this chapter focuses on the most important neuromuscular function in many sport performances, the ability to generate maximal muscular power, development, and program design will be addressed. This also includes advanced strength and conditioning techniques for developing power output. Power training. So what is power? Power can be defined as the applied force multiplied by velocity of the movement. So in short, power equals force times velocity. And as we remember from previous PowerPoints, force is the maximal amount of strength that we can develop. Work equals a force and the distance moved. Velocity is the distance divided by the time taken. So how fast we actually move in a specific movement. Power output for an athlete can range dependent on the training abilities and skills that are actually being conducted. For instance, power output for an athlete can range from 50 watts that's produced for a light cycle or a jog to around 7,000 watts produced during the second phase of a pull for a clean in weightlifting or Olympic lifting, as we'll talk about later. The main focus, again, for this chapter is to discuss maximal power output. That is, how can we produce the greatest amount of force to achieve maximal velocity at takeoff or impact during various types of movement, such as sprinting, jumping, changing direction, throwing, kicking, or striking. These movements are critical in sport performance. So to maximize the ability to perform these movements in the weight room and have greatest transfer effect onto the field is going to be key when we're developing a training program. On the previous slide, we discussed power. Power, again, is the applied force multiplied by the velocity of a movement. This is measured in watts, shown in W. So an example of power is a vertical jump. It's important to know there's different ways to measure a vertical jump. We have four images really on the left-hand side. We have what's known as the vertex, a jump mat, and a force plate. So this vertex is a very simple tool to use to be able to just simply measure jump height. We can get other variables such as power or force output from this, but it's going to be all estimated, so it's not exact measurements. The jump mat is not the best instrument for assessing jump height simply because it takes into account the time in air. So if you see the picture to the right, the vertical jump, the time in air is simply the time at which your toes leave the ground to the maximum jump height, and then the time that you return back to the ground. This jump height can be manipulated. Let's say if you pulled your knees into your chest, you have a longer jump height. Therefore, your jump, in theory, is higher. So it's not the best measurement. There is what's known as a force plate. It's a big, fancy, and very expensive bathroom scale, essentially. But this provides us with measurement of power, force, velocity, takeoff velocity, measurements that'll help us analyze a vertical jump appropriately. So what's the point? Why do I need to measure a vertical jump? In sport, there are a number of activities that require what's known as a triple extension or the skill itself of vertical jump. So we need to be able to understand jump height, what's important about it, and how to manipulate it to be able to improve our overall performance. So how should the force graph of a vertical jump look? So when we stand on the force plate, if we took our person, stood still on the force plate, counted down 3, 2, 1, and on 1 they jumped, did a vertical jump, and they landed, you would see this force plate data on the computer. So a force plate is connected directly to a computer, and we're able to receive this information. So you can see from 0 to 1,000, that horizontal line, this is where our person is remaining still. From about 1,000 to 200 milliseconds, that's where our person is dropping down into a squat. And as they shift into what's known as that triple extension of the ankles, the knees, and the hips, they're moving backwards, they're moving upwards for the vertical jump. At about 3,000, you'll see a flat horizontal bar. This is the time in air. This is how much time they've spent in the air during their jump. The major peak at about 400 milliseconds, that's where the person is landing back down onto the force plate. And then the remainder is simply the stabilization of the individual returning back to the ground. So jump height depends on both takeoff velocity as well as the position of the center of mass at takeoff. So if you're shifting backwards or forwards or to left or right, this will influence your ability to jump maximally, right? So takeoff velocity is simply between that 1,000 to 3,000 area where we're again leaving the floor. When our toes leave the floor, how fast are we leaving the floor? Takeoff velocity. In theory, the faster the takeoff velocity, the higher our jump height. So let's look into it a little bit more on the next slide. On the left-hand side, again, that's showing you a stick figure of where they are standing, where they're standing still, they're squatting down before the jump. F is initiating that takeoff velocity. So if you want to write down where F is, it says you can write a takeoff velocity. G is flight time because they are in the air. And H is where we're landing back down to the ground. That stick figure is correlating to the graph right below it in the blue line. Okay, so where A, you have that flat horizontal line. The letter D is corresponding when they're squatting down. So you see the line going negative. And as they stand back up, going into that triple extension takeoff velocity, the blue line is increasing. The steeper that slope is of that line, the faster the takeoff velocity. The more horizontal the line, the slower the takeoff velocity. G, that flight time, is where the bar is simply on the x-axis. And then we have returning back down to the ground onto the scale. We have H, where that big old spike is at the end, and then they're stabilizing. And then we have that flat line again, because they will essentially reflect back to where the A is. So as you can see on the right-hand side, we have force, power, velocity, displacement. Displacement is our jump height. So we're able to measure all of these variables and see how our jump measures during a vertical jump. So an athlete's jump when rebounding in basketball, for instance, shows the importance of the maximal power that is required in sport. So the height to which an athlete jumps for a rebound is purely determined by the velocity which he leaves the ground. Again, that's takeoff velocity. So at the bottom of the movement in the stick figure, like the letter D, at the bottom of the movement, the body stops momentarily. As the athlete extends into triple extension of the knees, the hips, the ankles, and leaves the ground, transferring from F to G, The body is accelerated upward to maximize takeoff velocity. This velocity is determined by the force of the muscles that can be generated against the ground. So again, takeoff velocity is key in maximizing jump height. Once the athlete has left the ground, he can no longer apply any force because we don't have contact with the ground, so there's no possible way. The faster the body is accelerated vertically, the shorter the time between the bottom movement and takeoff. So it's here is where we can appreciate the most important ability to maximize power. So what are the factors that contribute to power output? We just talked about vertical jumps, the output that we can get when we measure in a laboratory on a force plate, and looking at force, velocity, takeoff velocity, displacement, which is our jump height. But how do we maximize all that? It's awesome that we can see all this information, we can gather it, right? This will be similar to a needs analysis where we're gathering all that information. But now we need to discuss what factors actually influence the ability to improve output. So we have three mechanical properties of the neuromuscular system to determine performance. So one, the ability to develop a large amount of force in a short period of time, termed the maximum rate of force development, abbreviated MRFD. Two, the ability of muscle to produce high force at the end of an eccentric phase during an early concentric phase. So two is the transition from the squat to the triple extension. So again, number two is the transition from the downward squat to triple extension of the knees, hips, and ankles right before we go into our takeoff velocity phase. And three, the ability of muscle to continue producing high force output as its velocity shortening increases. Okay, so an example of this is when an athlete's jump, when they rebound in basketball, shows the importance of maximal power in sport. It also allows us to examine the mechanical factors that contribute to power. Again, this is the previous slide. So it responds more to specific power training than to heavy resistance training. So maximal power performance responds, again, training using a counter movement in which muscles are stretched first, then shortened. So this is simply stating eccentric, immediately followed by concentric, which is known as the stretch shortening cycle. On the next slide, we'll discuss this a little bit more as well. So again, these factors influence, and we'll talk about how specifically each component can contribute to maximal power and having its own window of adaptation and suggestions for the training program then athletes should actually use to maximize the greatest potential for adaptation. Stretch shortening cycle, abbreviated the SSC. This is also known as simply plyometrics. So the plyometric definition, or the stretch shortening cycle definition, is known as eccentric muscle action immediately followed by a concentric muscle action. Think of a rubber band. If you grab a rubber band and pull and immediately let go of it, it will go really far. Now, if I pull that rubber band again and hold it and keep holding it and hold it for a really long time and then finally release it, will it go the same distance? No. So again, going back to that definition, it must be immediately following that eccentric to concentric muscle action. Plyometric training results in an increase in the overall neural stimulation of the muscle, and therefore it's going to increase force output. In exercise physiology, we discuss GTOs, Golgi tendon organs, muscle spindles. This is the stretch reflex that we're talking about. We're now just simply applying the stretch shortening cycle and this loop reaction that our body has to maximize power. So plyometric training places considerable forces on the musculoskeletal system, right? We are utilizing the muscle, it's pulling on the tendon, pulling on the bone, and producing force, and then we have to land and absorb those forces. So therefore, the potential for injury is thought to be much higher for depth jumps, which should not be attempted for beginners. So simply a depth jump is from when you're jumping downward. So if you're on a box, stepping off and landing on the floor, that impact can be incredibly stressful and apply an incredible amount of forces upwards, up the chain of our muscular system, and should be something that be a skill that should be implemented down the line in programming and not right away. Novice lifters, novice athletes, beginners. A big key take-home message is that in order to be powerful, you must be strong first. You must have the strength foundation prior to training for power. It is critical that you have that slow and controlled strength prior to starting training for power. We just mentioned on the previous slide, strength is key prior to training for power. So what is muscular strength? It is simply the amount of force or torque a muscle can exert at a specified or determined velocity. Torque is just force rotating about an axis. So it can vary by muscle activation, for instance, quadriceps versus hamstrings, or muscle action. The amount of strength that you can produce per muscle is going to differ based on the size and how much you train or how much adaptation there has been applied to that muscle. So strength is commonly associated with slow speed or slow and controlled movements. Think 1 repetition max. If you're lifting as much weight as you can one time, are you going to move really slow or really fast? You're going to move really slowly. So again, strength, if we go back to our 4x4 that we discussed on the previous PowerPoint, strength doesn't tend to have more repetition than 6 because we are moving slowly. Therefore, the intensity is higher. As intensity increases, we know volume must do what? Decrease. Remember, those are inversely related. As intensity increases, volume decreases, and vice versa. So what's a limiting factor of strength? Muscle strength at slow contraction velocities, known as that sticking point, which is the weakest point in the range of motion. As slow movement velocities increase, then power output and athletic performance also improve. Now, we just said strength is key to developing power. Yes and no. Now, strength is not power. However, you need a foundational strength in order to train for power. It's just simply the process. That does not necessarily mean if you're strong, you will be powerful. Think of a bodybuilder. Because they have muscle, because they may be strong, does that make them fast? No. They simply have the foundation of strength that they have the ability to train at higher velocities to improve power. Therefore, strength, again, must be developed at slow velocities and gradually, meaning progression, that seventh critical variable, we're going to increase velocity to improve our power. If we're going to increase velocity, what does that mean for repetitions? What does that mean for intensity? Let's think through that. If we are increasing the speed of the movement, increasing the velocity of the movement, we have to reduce the load. So we're reducing the intensity so we can move through the movement faster. This is known as moving through the force velocity curve, which we'll talk about in a little bit in a few slides. But remember, when we get to that point, muscular strength is a part of that force velocity curve, but it's only a very small portion of training. Targeting power development. So the use of slow velocity, heavy resistance training for development of maximal power is justified on the basis that power is equal to the product of force times velocity. So force times velocity equals power, right? It has often been reasoned that the increasing of a 1 RM strength is sufficient to influence the potential of power output. If we maximize improvements in power performance in such athletes, it's because we are training both force, which is strength, and high velocity components, which again equals power. So the difference between untrained versus trained. Again, untrained, we must establish a strength foundation prior to training at higher velocities for power development. If you have athletes that are trained, it's not as critical to separate the two goals out, but to combine them into the same program, because you must train both force and velocity to improve power. Again, force times velocity equals power. You have to be able to train both of them and maximize both of them to improve this power output. So implement methods that decrease the time over the movement is produced. Think of a vertical jump. If someone were to jump the very first time, they might be slow, awkward. But if they do it over and over, train for strength, train for velocity, what happens to that vertical jump? It becomes more efficient, more fluid. They might be able to jump more vertical as opposed to in a rainbow fashion. This is, in turn, increasing power output, maximizing our rate of force development, which directly influences our takeoff velocity. Practical importance of strength and RFD, rate of force development. So remember, maximum strength is strongly related to RFD and power output. Why? Because again, power equals force times velocity. Therefore, strength is also a big component of improving power. Therefore, application of force at critical points during a movement results in superior performance. Stronger athletes can apply more force at critical points, resulting in superior performance. The stronger you are, the more force you can apply against the ground and propel yourself into the air. Stronger athletes can apply greater forces at absolute loads, meaning if you weigh more or if you're putting weight on your back or you have a weight vest. That's an absolute load. Therefore, again, because you are stronger, you can lift more, potentially increasing your velocity. Lastly, stronger athletes can produce force power outputs over a greater range of loads, resulting in superior performance. So again, this last point refers back to our force velocity curve, meaning we can apply force across this curve to maximize performance. Rate of force development shown in a graph. We've been talking about the rate at which we develop force. It's simply how fast are we producing force. So we're putting that in a picture, in a slope. You see a solid line pre-training and then a dotted line post-training. This is what we're looking at. We're looking from 0 of time to 200 milliseconds. This is where we generate our rate of force development. 200 milliseconds. 0 to 200 milliseconds is where we generate our rate of force development. That slope, the steeper the slope, meaning the more vertical the slope is, the faster the rate of force development we have. The more horizontal the slope, or the longer it takes to reach that 200 millisecond point, the slower the rate of force development. The goal, again, is to maximize strength, but also to maximize velocity. Again, to maximize power output. Post-training, this is what we want to see. We would like to see the dotted lines become more vertical, which in turn means we have maximized the rate of force development in a performance. In terms of training, we have a number of studies that have shown to improve power activity, such as like a vertical jump, following a strength training program. Because we keep saying that, yes, strength is important, but it doesn't directly translate to power. However, again, it's still critical to remember that strength, then power, or strength, then velocity to influence power is key. So there was 7% improvement in power when following a 24-week resistance training program. There was also a 21% improvement in vertical jump performance after a lighter load program, meaning higher velocities. So what does that mean? The combination of these two results in a very specific adaptation when we apply both heavy resistance training and high velocities to maximize power. In the graph that you see here to the right, we have this line that starts by the number 1, curves down by the word velocity, and then drifts off down below 0. That is that force velocity curve. So velocity is down by the right side, and maximal force is up by that top peak of that 1 right there. Maximizing force means we're really slow. That's why we're closer to the 0. As we move down the force velocity curve, we increase our speed, but the load decreases over time. And we'll talk about this again in a little bit. Although velocity-specific training adaptations are observed, right? We said that in the previous slide. Performance changes with trainings are not always consistent with this principle. This is what comes into play when we're saying resistance training, heavy resistance training, is not the only way to maximize power. It is one component because, again, power equals force times velocity. For instance, Changes in force-velocity relationships following a 10-week training program were similar in relatively untrained subjects exposed to either heavy resistance training or ballistic power training. Okay? The changes observed in the heavy strength training athletes were driven by improvements in maximal activation and muscle thickness. When you start a program, you're going to have neural adaptations that take place first, and then followed by the hypertrophy, the increase in muscle size thereafter. In contrast, the changes observed following ballistic power training were produced by movements in the rate of rise of muscle activation. So how fast we're sending this neural activation. So despite the differing nature of adaptations to each training stimulus, both resulted in significant improvements throughout this force-velocity curve, this force-velocity relationship. What's my point? It appears that training adaptations of a single factor, meaning only high force or only high power, high velocity, occur only after a base level of strength and power has been achieved. For instance, a novice lifter. Going back to novice lifters should lift a single factor, one and then the other, to be able to combine the two to maximize power. Here is your force velocity curve that we've been talking about so much. In the image, we have force on the y-axis, velocity on the x-axis. At the corner where 0 should be, if we move directly from 0 up to the top of force, that's telling us that we have high force. We're producing a lot of force, but at very low velocities. If we go along the x-axis, go all the way out to the word of velocity, but still close to the 0-axis marker, we're at really high velocities, but at low force. So again, force and velocity have a relationship that's inverse. But the combination of these two, velocity times force, maximizes what's known as this power output. So the solid line represents before training, but after training, after we develop our rate of force development, after we do heavy resistance training, after we complete training for high velocity, we're moving this curve up and to the right. So heavy resistance training moves the force velocity curve upwards, but that's it. Only upwards. That is why we need to also move it to the right, which means we're maximizing our velocity. Therefore, we need to include high velocity movements. And therefore, the goal is to maximize power by moving this curve up and to the right. If you want to be a strength coach at any level, this will be your life. This is your ultimate goal, to maximize your athlete's force production and velocity production, ultimately resulting in maximizing power output. So your goal is to always shift the force velocity curve in an effective training program both up and to the right. If you do this, then you are therefore maximizing power output. So we talked a lot about why, but how? There are 4 different ways that we can maximize power development. 1, heavy resistance training, which we talked about a lot. Now, I'm going to throw some vocabulary at you. Heavy resistance training, this is known as power lifting. Hold on to that thought because it can get confusing. Number 2, ballistic resistance training. 3, plyometrics. Remember our definition. Eccentric muscle action. Immediately followed by concentric muscle action. This was the rubber band example. And then 4, weightlifting, which is known as Olympic lifting. So number 1 and 4, they can get a little confusing. So I broke it down in a table for you. Heavy resistance training is known as power lifting. Although it is confusing in terminology, the 3 big exercises for power lift is bench press, squat, and deadlift. All 3 of these are conducted in a slow and controlled manner. Now, weightlifting is known as Olympic lifts or Olympic lifting. We have 2, the clean and jerk and the snatch. These movements are conducted quick at high velocities and should never be right next to the individual when someone is lifting Olympic lifts. When you're powerlifting, you may have a spotter for a bench press or a squat. However, you will never have a spotter for a weightlifting Olympic lift, for the clean and jerk or the snatch, because they're explosive, because they're done at maximal velocity. The bar is being thrown around from the floor vertically upward until you catch it onto your shoulders and then push it overhead, or where you're going with the snatch, from floor to overhead. So let's talk about this a little bit more. So the methods in developing power in athletes include, again, heavy resistance training, that's slow and controlled movements, because in order to be powerful, the athlete must be strong first. Seeing a pattern here? Heavy resistance training, again, also known as our powerlifting. So the general rule, athletes should be able to generate 3 times the muscle tension required during the sporting performance, meaning the neuromuscular system can generate the greatest amount of power when it's working against 30% of maximal load. Now, if you were to go back to slide 11, you'll see this curve that is an inverted U. When it crosses over that force velocity line and making an X, that's 30%. So what I'm saying is, if someone can lift 100 pounds maximally, one time, this is their 1 RM, 30% of their max rep is 30 pounds. Therefore, the neuromuscular system can generate the greatest amount of power at 30 pounds. They can move 30 pounds fast and explosively. If they increase their 1RM to 105, 110, then again, the ability to increase your power output goes up to from 30 to 35 to 40% of weight lifted at that point. So although the use of heavy resistance training is vital in development of strength and power, further training-induced movements in maximal power requires the involvement of other, more specific movement patterns. So the second one, ballistic resistance training, involves the trajectory of movements. For instance, a jump squat. You are the trajectory. You are propelling yourself into the air. Or you're throwing an object, such as a barbell, where you're throwing a bench throw, or a medicine ball, with the goal of accelerating through the entire range of motion. What does this require? Concentric velocity, force, power, and muscle activations are higher during ballistic movement than during similar traditional heavy resistance training lifts. because we need a faster response of muscle activation. Ballistic resistance training is very sport specific and may result in appropriate adaptations that allow for the greatest transfer of performance in comparison to resistance training alone. Again, that force velocity curve on slide 13, you need to work all throughout this curve. So 1 through 4 that we're talking about right now is providing the blueprint for us to program and develop a program that goes along this entire curve from maximal strength to maximal velocity to ultimately reach our goal of moving that curve up and to the right. So number 3, plyometrics. Again, plyometrics are it's a training modality that involves exercises in which athletes perform rapid stretch shortening cycle movements. Here your definition again, an eccentric muscle action immediately followed by a concentric muscle action. An example of this is our vertical jump, including both unilateral, single arm, single leg, and bilateral, when you're standing on both legs or utilizing both arms at the same time. Catch, throw, push-up, bounding, hopping, jumping variations. Plyometrics can be implemented in multiple ways. How we improve plyometrics is by overloading the applied force, by increasing the stretch rate or load. Number 4, weightlifting. Again, this is known as our Olympic lifting. This is our clean and jerk and our snatch. They're explosive movements. There were a number of variations of these exercises that you'll hear about, you might have heard about already, but we have power clean, which is the power is referring to the starting position. The hang is the ending position. We have power snatch, hang snatch, high pull, hang pull, and push press. Weightlifting requires athletes to accelerate throughout the entire propulsive phase, similar to ballistic, whereas our power lifts, which is the heavy resistance training, we're not accelerating through the entire phase. We're slow and controlled, where we actually might reach a sticking point with heavy resistance training. So our acceleration is going to change throughout the phase. Again, number 4, weightlifting requires athletes to accelerate the entire time. Therefore, the inherent high force, high velocity nature of weightlifting movements creates the potential for these exercises to produce large power outputs across a variety of load conditions. Because this is an online recording, I want to help illustrate the explosive reaction of Olympic lifting. As a reminder, Olympic weightlifting movements, such as the snatch and the clean and jerk, require the athlete to accelerate the barbell throughout the propulsive phase, providing a good stimulus neurally and muscularly for power development. As you can see for the clean and jerk, you start with the barbell touching the ground by shifting the barbell upwards in a vertical motion, moving through that triple extension of the ankles, the knees, the hips, and ultimately jumping, which is really illustrated in the middle picture of the snatch, where you see the ankle, the knee, and the hip really in extension. It's essentially you're doing a vertical jump with weight. You're pulling that barbell up towards the shoulders and then dropping underneath the barbell and racking it on the shoulders for the clean and jerk. And then eventually you're going to push the barbell overhead for the jerk phase, illustrated with the red barbell weights. The snatch, that's illustrated in the black and white. The top is your starting phase, but instead of catching it at the shoulders like you did for the clean, you're simply continuing the barbell momentum and catching it overhead in an overhead squat position. A take-home message for training methods for power development with volume. So volume for all, including muscular strength, our ballistic, plyometrics, and weightlifting. Again, weightlifting meaning the clean and jerk as well as the snatch. Muscular strength, we're talking about the power lifts, which is our squat, deadlift, and our bench press. These movements are all very complex, which require a large amount of energy and neuromuscular communication, meaning the communication between the central nervous system, brain, and spinal cord, and the communication between our central and our peripheral, which communicates with the muscle. Therefore, the greater amount of the reps, the greater the fatigue. We should never have weightlifting power, meaning our clean and jerk and our snatch, to ever go over 6 repetitions. The fatigue and the taxing of the nervous system without adequate rest will likely lead to injury. So the focus. Resistance training for strength translates to gains in power performance, but not immediately. You're at the top of that force velocity curve. We have to work our way down as well. A combination of strength, ballistic, plyometrics, power, which is our high velocity, weightlifting, that focuses on the entire force velocity curve is absolutely critical to maximize the greatest transfer of performance from weight room to the field. So we have to talk a little bit about the programming and tapering and recovery to optimize power performance. As we've discussed, a wide range of neural and muscular factors must be combined in order to optimally produce maximal power. Force times velocity gives us our power. Certain training modes affect these components in a negative manner. So fact, aerobic work negatively affects anaerobic performance. If we have our football athletes run a long distance continuously, this will negatively influence the muscle's ability to produce large amounts of strength and large amounts of power. Fact, training only strength can negatively affect power performance. Again, using your bodybuilder as an example. They're training for strength to maximize hypertrophy, increase in muscle size. This does not necessarily translate to power output. In order to be powerful, you must train for power. You must include high velocity movements to effectively influence power performance. It's altering the type of fiber recruited and architecture of the muscle pennation in the opposite direction desired for power production if you only train for strength and not include a high velocity component. Therefore, when power is key in any sport, we must think about tapering our programming. So if you are programming for someone, tapering means to essentially slow down or take away up to 4 weeks prior to season or a competitive season to make sure we avoid power loss. So power lifting, squat, deadlift, bench. We're not taking it away, but we're simply reducing the amount of sets per week. During season, weight room sessions are reduced to roughly twice a week because we have games, because we have actual session and training sessions on the field. Therefore, during those 2 sessions, you should include less volume of our strength, but include more volume of power, which is our high velocity movements, or a combination of the two. So selecting a load, intensity, and velocity for power development. High versus light. So heavy loads, greater than 80%, are also commonly used in power training programs, incorporating ballistic and weightlifting movements. So weightlifting, again, our clean and jerk and our snatch, can be done at very high loads and is highly suggested to do so to improve maximal power. So based on 2 theories, one, the force-velocity relationship, which is the mechanics of muscle action, eccentric, concentric, isometric. And theory 2 is the prescription of heavy loads. What intensity and volume are we utilizing? Refer back to our 4x4 for this. Light loads, the high movement velocity, RFD, and power requirements of ballistic power training involving light loads are theorized to elicit adaptations in neural activation patterns and intermuscle coordination that drive those improvements. So the take-home point, training with light loads is recommended for athletes who are requiring high power outputs during fast movements against a low external load, such as sprinting, jumping, throwing, or even striking. On the previous slide, we discussed heavy and light loads. So essentially, we are now discussing power output and how it varies dramatically as a load changes for an athlete to accelerate during a movement. We have to discuss optimal, combining, and velocity specific, which is essentially discussing the previous slide and now taking it a step further. As previously mentioned, we said power is maximized at approximately 30% of our maximal force. Remember that example of a 1RM where your athlete can lift 100 pounds one time. 30% is 30 pounds. So since improvement in power are most pronounced at the load using in training, training with optimal loads provides an ideal stimulus to elicit an increase in maximal power output for specific movements. So it's important to know what your athlete can lift maximally to appropriately program for maximal power. Combining loads, the combination of ballistic and strength, such as jumping and heavy squatting rather than the combination of ballistic and light loads and heavy loads. There's a number of different ways that we can implement this. Velocity specific. In order to maximize the transfer of training to performance, it is absolutely imperative that athletes train with loads that allow for similar movement velocities to those typically encountered in their sport, but not 100% of the time. We still need to combine those loads. So additionally, athletes should attempt to perform these exercises with the goal of generating maximal force as rapidly as possible. So maximal effort, no matter the load, no matter the skill, no matter the activity, is always key when training.